Hello, Vanakkam. Welcome to the Electrical Engineering Examples channel. In this channel, the focus is on providing detailed solutions for various example problems with a goal of maximizing exam performance. In this video, I will be focusing on analyzing a circuit or a system that comprises of a three-phase transformer feeding a load. So let us go through the question a bit more carefully. There is a 100 MVA, 220 kV by 222 kV, three-phase Y delta transformer, which has an equivalent series impedance of 1 plus J5 ohms per phase, referred to the high voltage side. Okay, so 100 MVA, 220 kV by 22 kV, three-phase Y delta transformer has an equivalent series impedance of 1 plus J5 ohms per phase, referred to the high voltage side. Now, the transformer is supplying a three-phase load of 100 MVA, 0.8 power factor leading at a terminal voltage of 22 kV on its low voltage side. So there is a load, three-phase load, which is a leading power factor load. So it's a capacitive load that is being fed from the low voltage side of the transformer, which is the delta connected side. And incidentally, the terminal voltage across the load is same as the rated voltage of the transformer secondary. Okay. So 22 kV is the same as the transformer secondary rated voltage. Now the high voltage side, which is the Y side of the transformer, is supplied from a feeder. Feeder basically means power line with an impedance of 0.5 plus J1 ohm per phase. So the high voltage side of the transformer is being supplied from a power line which has a series impedance of 0.5 plus J1 ohm per phase. Determine the line-to-line voltage at the high voltage terminals of the transformer and the sending end of the feeder. So what we need to find out is the line-to-line voltage that appears at across the high voltage side terminals of the transformer. If the transformer were ideal transformer, then we should have got 220 kV because the low voltage side is supplying 22 kV. But because the transformer has a series impedance, there is going to be some voltage rise when we go from low voltage side to high voltage side. Therefore, the high voltage side voltage must be greater than 220 kV is our expectation. Okay, we can look at this problem quantitatively and find out what exactly is the high voltage side line-to-line voltage value. And then using the same explanation, the sending end of the feeder will also be higher than this line-to-line voltage because the feeder has its own impedance. Okay? So as always, in order to solve such a problem, the first step is to draw a schematic representation of the system. Okay, so there is a three-phase transformer which has a Y connection on the high voltage side. And then the two lines indicate the magnetic core of the transformer. Then there is a delta connection on the low voltage side. Okay. This delta connected side is feeding a load We do not know the connection type of the load. Okay, so we are going to assume a connection type. I'm assuming the connection type of the load to be Y connection, and the load, I'm going to draw it using a box because it is a capacitive, resistive capacitive load. Okay. So I'm just going to indicate this explicitly here. The load is assumed to be Y connected. Of course, you can assume the load to be delta connected as well. It will not change anything here. So there is a three-phase transformer which has 220 kV on the high voltage side and 22 kV on the low voltage side. And please note, these are line-to-line voltages. So this is, if 220 kV appears on the high voltage side, ideally speaking, the low voltage side should get 22 kV. That is what it means. Okay? And this is a 100 MVA transformer. So 100 MVA, 220 kV bar, 22 kV is the rating of the transformer. And the line-to-line voltage that is appearing across the load terminals is specified to be 22 kV. This is already specified, okay, in the problem. Now, in addition to this, the problem, there is also mentioned that the primary side or the high voltage side of the transformer is being fed by a feeder which has a series impedance of 0.5 plus J1 ohm per phase. So this is 0.5 plus J1 ohm. Because it's plus J, I'm using an inductive drop or inductive reactance. If it were minus J, I would have had a capacitor in series. Okay. So 0.5 plus J1, 0.5 plus J1. And these are all ohms. That is the impedance of the feeder. So the sending end of the feeder is basically the points to the left of these impedances. So this corresponds to sending end of the feeder. So what we need to determine is the voltage at the sending end, the line-to-line voltage at the sending end, and the line-to-line voltage at the high voltage side of the transformer. So this voltage, so let me just label it using different color. So we need to determine the sending end line-to-line voltage and the VHV, the high voltage line-to-line value. Okay. So these are the two quantities that we need to determine, and we are going to look at it. Before we go there, we also know the rating or the operating condition of the load. The load is a 100 MVA load that consumes power of 100 MVA at 22 kV, and it has a power factor of 0.8 leading. Okay, very important. So we know these details. So this is the first step in solving such a problem. We represent the problem pictorially with all the useful information. As a next step, so step 2, we always start from the load end. We will solve for the current consumed by the load. Okay. So it is given that the load is consuming an apparent power. Okay, it's very important. So S3 phase at the load end is equal to 100 MVA. So this is the apparent power. Power factor is 0.8 PF, 0.8. It is leading power factor. From these two information, we can calculate the real power P three phase, which is 100 MVA into 0.8, which is 80 megawatts. Now, the real power consumed, the three-phase real power consumed can be used to solve for load current. So we know that P three phase is equal to root 3 to V line to line into I line into power factor. So that is root 3 into the line to line voltage is 22 kV. So line current is something that we are yet to determine, and power factor is 0.8 power factor, which is 80 megawatts. Okay. Now, if I rearrange this expression, I will get 80 megawatts, or let me write the line current, which is the unknown variable, as 80 megawatts divided by root 3 into 22 kV into 0.8. Okay. Now, incidentally, this ratio of 80 megawatt over the power factor 0.8 is nothing but the apparent power 100 MVA. So in fact, I could have written the line current directly as I line is nothing but 100 MVA divided by root 3 into 22 kV, where 22 kV is the line to line voltage. So I need not have solved for the real power at all, because the moment I know apparent power, real power divided by power factor is apparent power. So I could have easily used this expression directly without going through these steps. Okay. So let us find the value of IL, and please note these are all magnitudes. So if you want, you can indicate that this is a magnitude by explicitly drawing the magnitude symbol. 100 MVA divided by root 3 into 22 kV. When I do the math, I get 2624.32 amperes. So this is the magnitude. We know that the current will be a complex number. What I mean by that is it's a phasor which has magnitude and an angle. So the current phasor is IL at an angle of cos inverse of the power factor value. But because this is a leading power factor, we will have a negative sign in front of the angle. And therefore the theta is, or IL phasor is 2624.32 at a negative angle of, oh, so this is a leading power factor, so it must be a positive angle, sorry. This is just a positive angle, cos inverse of power factor value. So this must be a positive angle, not a negative angle, because this is a leading power factor. So if current is leading the voltage, therefore the angle will be a positive quantity, and that is what we are taking it. So cos inverse of 0.8 is 36.87 degrees. So this is the value of the complex current consumed by the load, and this is what we need to find out as step 2. Okay, very important. So in step 1, we have drawn the pictorial representation of the system. In step 2, we have calculated the complex current, which involves both calculation of the magnitude and the angle. And because leading power factor means angle will be positive for current. Okay, leading power factor results in positive angle. That is something you need to keep in mind. Okay, so this is step 2. So now we can go backwards and we can indicate. See, this is the line current that we have solved for. So the line current IA is going to be equal to 2624 approximately at an angle of plus 36.87 degrees. Okay. IB will be the same magnitude, but the angle will be displaced by negative 120 degrees with respect to 36.87. IC will be same magnitude, but the angle will be displaced by another one or plus 120 degree from this angle. Okay, so you need to remember that. So we have calculated IA value. IB, IC can also be synthesized. So this is step 2. Now we know the line voltage or line to line voltage and the line current of this associated with the load. Once we know these two information, we will now go to step 3, which is to look for whether there is any delta connection in the system. And if there is any delta connection, we are going to convert into equivalent star. So we are going to redo the system. Step 3, convert all delta connections into equivalent star or equivalent Y. And since we have assumed the load to be Y connected, we just have to convert the secondary of the transformer into equivalent Y. So let us quickly redraw the circuit. This is feeder for phase A, phase B, phase C. Each one has the same impedance. So I'm just going to write it only once in ohms. And then I have the primary of the transformer, which is Y connected by default. So I have my primary being fed from the feeder. And then on the secondary side, it was originally delta connected, but now I'm going to redraw the delta into using its equivalent Y. Okay. So the original connection was something like this. Okay. And from here, we have the 3 lines that are brought out. Across the line to line, the voltage remains 22 kilovolts and the current is 2624 at an angle of plus 36.87 degrees. In fact, you can approximate it to 37 degrees if you want. Shouldn't matter. Okay. And then we have the load, which is also Y connected. And this is an assumption that we made in the initial part of the problem. Okay. So this is an equivalent, the red color winding is an equivalent Y for an actual delta connection. And once we have an equivalent Y, we know that the phase voltage of this equivalent Y will be, the phase voltage is going to be 22 by root 3 in kilovolts. So that is the phase voltage of this equivalent Y winding. So once we have this pretty much brings it down. From here, we can draw the per phase equivalent circuit or per phase representation. So step 4 is sketch the per phase representation. And use the transformer impedance. See, please note that until now, these are all practical transformers. So the symbol that I have drawn here is that of a practical transformer. So that means this transformer has some losses. It has a series impedance associated with it. We have just drawn the symbolic representation. So this is a transformer symbol. It is not the equivalent circuit. In step 4, what I'm going to do is I'm going to use the equivalent circuit representation or equivalent circuit model of a single phase transformer along with the per phase representation. So you need to keep in mind that in this step we are doing two things. We are going for the per phase representation of the circuit or the system. In addition, we are introducing or we are representing the transformer using its equivalent circuit model, okay, of the transformer, not the transformation. So if we do that, what we will have is only one phase which has 0.5 ohm plus J 1.0, which is the impedance of the feeder. This is phase A, let us say. And then we will have only one winding on the primary side or the high voltage side. Then we will have so this is just a symbol of the transformer. But now since we want to include the equivalent circuit model, the equivalent circuit model will have, okay, just let me so the equivalent circuit model of the transformer is another impedance. And as per the problem statement, if I go back to the slide which introduced the problem, the equivalent circuit impedance of the transformer is 1 plus J5 ohms referred to the high voltage side of the transformer. So when I introduce the equivalent circuit impedance 1 plus J5, it must be connected to the high voltage side of the transformer. So this part, this series impedance, in fact, I can use a different color just to make sure that you get this clearly. So this series impedance represents the equivalent impedance of the transformer. And whatever is left out to the right hand side is the ideal transformer, which will have a turns ratio in proportion to the ratio of phase voltages. So what is the phase voltage of the primary to secondary side? Because the primary was star connected, if 220 over root 3 voltage appears here, the secondary side should get 22 over root 3 kilovolts. So the turns ratio is nothing but 10:1 for this ideal transformer. Okay, so you need to go back and recollect that whenever we want to replace the symbol of a transformer using its equivalent circuit model, you will have a series impedance along with an ideal transformer which has just the turns ratio. Okay. And this secondary side of the transformer is now feeding a load, just one phase of the load. And what will be the current flowing in the system? The current IA is going to remain intact, which is 22,624 at an angle of 36.87 degrees in amperes. Why is the current same? Because if I go back, this is a Y connection. So the line current is going to be the phase current of this equivalent Y winding. Okay. So that is why the phase current of this newly drawn red color winding remains the same as the line current, because this is a star connection. So in star connection, line current and phase current are one and the same, because if I apply KCL at this node, whatever current enters the node has to exit. So if I know the current leaving the node, I know the current entering the node, which will be equal to the winding current. So these things I have sketched not just the per phase representation, but I have also introduced the equivalent circuit of the transformer. So the equivalent, so this part now is actually the equivalent circuit representation of the transformer. It has the equivalent series impedance along with an ideal transformer with just a turns ratio. Okay? So it's very different from just a symbolic representation of a single phase system. So once we have this, all we have to do is we have to apply the transformation. We can synthesize the current flowing on the left hand side of this single phase system. So step 5, in step 5, let me call this as the current IHV or I capital A, because this is the HV side. In step 5, solve for IA first. Okay. IA is equal to IA divided by the turns ratio, which is 10, which is 262.4 at an angle of 36.87 degrees. So current will be 1/10 on the high voltage side, whereas the voltage will be 10 times. Okay. So this voltage is 22 divided by root 3 is the voltage that is appearing here. So the load voltage is IA, and just let me make this compact so that I can introduce one more variable here. There is another voltage here which we want to remember. So this is the reflected voltage of the load represented on the high voltage side or on the primary side of the transformer. So this is going to be VA dash, okay. And the current here is going to be IA dash, which is equal to IA. And VA dash is going to be equal to 220 divided by root 3 kilovolts. Why? Because the load voltage is already known, and it is 22 divided by root 3 kilovolts. That's the voltage across this red winding, if you recollect. Okay. So once we have drawn this, I am reflecting the quantities on the right hand side using an ideal transformer and bringing them to the left hand side. See, please note IA is the reflected current IA dash actually, and since it is the same current, I am using IA as a symbol. Okay. So the high voltage side current will be the reflected current from the low voltage side IA dash, and the voltage across the ideal high voltage side coil is going to be VA dash, which is 220 kV over root. Now we can make the voltage across the load as the reference voltage. So the vector representation of this will be an angle 0 degrees. Because the load voltage is considered as the reference point. Because the load voltage is reference, the current angle is plus 36.87. If the load voltage had an initial angle of 5 degrees, then the current will be 36.87 plus a 5 degree. Why? Because we have just determined the power factor. So in fact, I should go here. When I say cos inverse of 0.8 is 36.87 degrees, I have assumed here already that voltage across the load is the reference phase. And because a reference means 0 degree, that is why the angle of current is exactly equal to 36.87. If the voltage across the load had an angle of 5 degrees or 10 degrees, then we need to add that angle to this value. Okay? So we have VA dash, we have IA. So now we can calculate our transformer's primary voltage, which will be the voltage appearing here. Let me redraw the single phase system with a new set of quantities. This is the feeder. This is the transformer impedance. This is the ideal transformer with a turns ratio of 10:1. And then we have the load which consumes a particular current, and the voltage across the load which is acting as a reference is 22 divided by root 3 at an angle of 0 degree in kilovolts. The current consumed by the load is 2624 at an angle of 36.87 degrees in amperes. The voltage at, so this is a 10:1 transformer. So the reflected voltage VA dash is 220 divided by root 3 at an angle of 0 degree in kilovolts. And the current that is reflected, which is the series current in this circuit, is 262. The current in this circuit, which is 262.4 at an angle of plus 36.87 degrees. And the impedance of the transformer is 1 plus J5 ohms. And the impedance of the feeder is 0.5 plus J1 ohm. Okay. Now what we can determine is the voltage across the primary of the transformer. So this is 1 point. So this is going to be my VHV per phase voltage, and this is going to be my V sending end per phase voltage. So let me just write this as VHV phase, V sending end phase. So as per the problem statement, we need to solve these two voltages. So once we have drawn this single phase system and reflected the quantities from the secondary side onto the primary side of the ideal transformer, we can apply KVL to the loop and we can easily solve for VHV per phase is nothing but, so this will be a complex number. It will be VA dash plus IA, all are complex numbers, times 1 plus J5. Okay, that is 220 divided by root 3 at an angle of 0 degrees in kilovolts plus 262.4 at an angle of 36.87 multiplied with 1 plus J5. So if you solve that, the high voltage side per phase voltage is going to be, so let me quickly do the math, 220 kV divided by root 3 . 220 kV divided by root 3 at an angle of 0 degrees plus 262.4 at an angle of 36.87 into 1 plus 5J So that is found to be, the phase voltage is found to be 126.445 kilovolts at an angle of 0.547 degrees. So it's very close to 0 degrees, an angle of 0.547 degrees. Let me recheck this value. So this will be in kilovolts. So 262.4 at an angle of 36.87. When this number is multiplied with 1 plus 5j, I have a complex number, and I need to add that with 220k divided by root 3, and I get 126.445 kV at an angle of 0.547 degrees. So this is the primary side or the high voltage side phase voltage. Now the line to line voltage of the HV side, VHV line to line, is going to be root 3 times the phase voltage So that is, and the line to line will always be leading the phase voltage by an angle of plus 30 degrees. So I need to add an addition of angle of 30 degrees. So it will be, the magnitude will be root 3 and the angle will be plus 30 degree. Okay. So let me just re-represent this slightly differently. Root 3 at an angle of 30 degrees into VHV phase. So that will be, the magnitude will be amplified 126.445 into root 3. This is 219 kV. Okay, and then angle will be 30.547 degrees in kilovolts. Okay. Okay. Very important, this result. See, we started with the assumption that when we have a series impedance in the transformer, the high voltage side should be greater than 220 kV, because ideally speaking, if there were no series impedance of 1 plus j5, whenever 22 kV appeared across the line to line of the transformer, which means the phase voltage is 22 divided by root 3, the phase voltage across the transformer primary would have been 220 kV divided by root 3. Okay? Or the line to line voltage would be 220 kV itself under ideal circumstances. But because we had introduced this equivalent impedance in series, because of this circled impedance, we expected the VHV should be greater than 220 kV. But we are getting an answer of 219 kV. Does this make sense? We have to think deeper. The load being capacitive in nature is resulting in a leading current. And whenever we have leading current, it is likely that the load side voltage will be greater than the primary side voltage or the high voltage side voltage. Okay. In fact, this can be a problem in long transmission lines. We will learn about that a little bit later in the course. But even though the magnitude of the high voltage side line to line voltage is less than 220 kV, it is not an incorrect answer in this case, because the load is consuming leading power factor current. If the load was an inductive load, then we should not have got such a low number for the line to line voltage on the high voltage side. We should have got a value greater than 220 kV. Okay. So whenever we have a capacitive load, it is okay to get this number, but if we have an inductive load, we cannot get that. Then we will go one step ahead and we will try to solve for the sending end phase voltage. The sending end phase voltage as a vector is going to be VH, V phase voltage, plus IA as a vector times 0.5 plus J 1.0, which can be solved. So VHPV is just obtained previously. IA is also known 262.4 at an angle of 36.87. When it's multiplied with 0.5 plus 1J, you get a complex number, which is a voltage drop. And this voltage drop must be added to 126.445 at an angle of 0.547 degrees. And when we convert it, I think I made a mistake. Let me quickly redo the calculation. 126.445 kV at an angle of 0.547 plus 262.4 at an angle of 36.87 into 0.5 plus 1I. So it's very similar, 126.4 kilovolts at an angle of 0.678 degrees. So the line-to-line voltage of the sending end will be √3 at an angle of 30 degrees into Vs phase vector. So that is going to be answer multiplied with √3 at an angle of 30 degrees. That's going to be 218.93 or 924 at an angle of 30.678 degree in kilovolts. Because of the leading current, the further we go to the source from the load, the voltage magnitude continuously decreases. And this is what I mean in power systems when we have a capacitive load, and if the source is too far away from the capacitive load, then there will be a significant voltage difference and the load will be at a higher potential than the source, which is not necessarily a good thing in a power systems. Okay, so these two results actually are very important. The line-to-line voltage on the high voltage side of the transformer, which is this value here, and the sending end voltage line-to-line value, which is this value here, clearly shows with the capacitive load, it is possible to have a sending end value or the source value lower than that of the load value. So the load value when reflected onto the primary side or the high voltage side is 220 kV, but the sending end voltage is only 218.9 and the primary side of the transformer is having only 219 kV. Okay. So the load voltage is greater than the source voltage, and this is due to leading current. Okay. So this is how we will be solving a problem such as the one specified, where we had a three-phase transformer connected and feeding a load balanced three-phase load. Okay. I hope this helped you learn the steps associated with solving such a problem. If you have any questions, you can always type in the comments section. Thank you.